Alright, welcome to lesson 3. Here we're going to look at exponential functions, and notice that in our discussion of derivatives we have really just looked at polynomial functions. And so if you think about, think back to kind of all the different function types that we know how to use, polynomials, while they're really important, they're not by any stretch of the imagination the only functions out there. So now we're going to start looking at some different function types and finding the derivative of these functions as well. Okay, so before we dive into exponential functions, there's a couple of things that we want to remember. And the first is Euler's number. It's a constant value represented by the lowercase e for Euler. And Leonhard Euler, he discovered this value when he was searching for the right base of an exponential function in order to think about things that are continuously compounding. And we actually talked about this briefly in Algebra 2, and I think I mentioned it over the Summer Academy videos as well, which is that this is actually defined, the way that he defines this number is using a limit. And so now we can truly appreciate how this number is calculated. So it's calculated by taking the limit as x approaches positive infinity of 1 plus 1 over x to the x. And hopefully this setup here kind of helps you understand why it's going to be continuously compounding if you raise something to, or if you take e as your base and keep multiplying by that over and over again. Because what this is doing is, if you think of multiplying some sum of money by 1 plus a really small fraction, like just as an example, 1.1. When you multiply some sum of money by 1.1, what you're doing is increasing it by 10%. You keep the original 100 and you add on the 10%. And so what this is saying is, what would your base be if you were making the value that you kept adding on really small, right? So 1 plus very, very small fraction. But you did it infinitely many times. In other words, you're compounding infinitely many times, so that you're not just taking the interest at the end of the month or the end of the year, but that you can actually be taking the interest at every instant, always, and so that it adds up to some total amount of interest at the end of some term. And you don't need to understand all of this. I just wanted to give you a background, and obviously if you're curious, you can go take a look, Google it and check out. I'm sure there's a good Khan Academy video on this topic. The important thing is that we know the value that it is equal to, or approximately equal to. It's an irrational number, so it goes on forever and ever, and approximately equal to 2.718. It goes on for much longer, 2.71828 something, so I can't remember the next 5 digits, but 3 digits is plenty for us to understand the value of e, and we'll discuss it a little more when we get into exponential growth and decay, which we'll talk about. But for now, important to know that that's the number e. The next thing is logarithms, and so log base b of x. This is, if you compute this value, what you're trying to figure out is the exponent that you must raise b to the power of to equal x. And so another way of writing this expression, if this is equal to some value a, then what you're saying is that b raised to the a power will equal x. Okay? So just a reminder, and what you want to just remember is that log base b of x is finding the value that you raise b to in order to get x. Natural log of x is taking the log where the base is e of some value x. And so here what you're asking, as you're trying to find, is what must you raise e to the power of to get x? And so if this were equal to a, then that's the same as saying e raised to the a power is equal to x. Okay, so a couple of things to remember and keep in mind so that when we utilize them over the course of this lesson, they will make sense to you. All right, so it's time to discover the derivative of e to the x. So to help you understand what it will be, it's first going to be really helpful to sketch a graph of the function and use our knowledge of how the relationship works between a function and its derivative to kind of think about what the graph will look like. So go ahead, copy this down, work through parts A first, and then part B. Use the hints in part B, and go through it and really think about each step. Try and use some logic as far as like what you're going to need to do in order to evaluate this limit. And don't be afraid to go into your toolbox of ways for evaluating limits and experiment a little bit, because you are totally capable of deriving the derivative for e to the x on your own. So here's a graph of e to the x, usable from alpha. You could use your calculator. And eventually we'll use this function so much that you'll will hopefully memorize just the shape of e to the x. So what my goal is to sketch a graph of the derivative. And so the derivative is just the slope of the function at any point. And so what I'd like to do is analyze the slope of this function in a way that will allow me to sketch the derivative. So using our method of constructing a sign chart for the derivative, what I can do is look for critical points, right? Where is the slope going to be 0? So let's just start on the right side of the y-axis and positive x values. Think about what the slope is as we move to the left. So here clearly the slope is positive. Positive, positive, positive. Not very close here. It's very easy to tell the slope is positive. What happens is I am getting into the negative x values. Well, e to the negative 1, for example, is 1 over e. Still a positive value. 1 over e to the negative 2 is 1 over e squared, which is going to be a little bit smaller than e to the negative 1, but still positive. And we can tell that if we continue this on as we move to the left, the more negative the value gets, the smaller the value of e to the x. Meaning that every time I move to the right, I'm going to be getting a bigger value, which means the slope is always going to be positive. So it doesn't matter how far I go out here, I'm always going to be increasing ever so slightly as I move to the right. Meaning two things. The first is I'm never going to actually have a perfectly flat slope. There's never going to be a place where my derivative is 0 or intersects the x-axis. And further, it means that the slope of e to the x, in other words, the value of my derivative, is always going to be positive. So now we can think about sketching the graph of this function. And if you haven't done so already, pause and try it yourself. The derivative is always going to be positive. It's always going to have a value above the x-axis. Let's think about how positive it will be further to the left. Notice that as we move further to the left, it seems to be flattening out. E to the x, that is. So the derivative, which measures the slope, should also be getting smaller and smaller, because the flatter the function is, the less the slope. We know it's positive, and we know it's going to be a very small slope as we move closer and closer to negative infinity. Okay, keep that in mind. Now, as we move to the right, we can see that the slope is increasing. Our function is beginning to get steeper and steeper, which means that the slope, the derivative, is also going to be increasing in value. So notice what we've just discovered. As we move to the left, the derivative is getting closer to 0, but never actually touching it. And as we move further to the right, the derivative is going to increase in value, increase in value, and increase in value. So what you've noticed is that the derivative seems like it's going to be very, very similar to the original function. So when we go and actually look to find the derivative, we would expect to find something that, it could be eerily similar to the original function. So we should be expecting something very similar, if not exactly the same as e to the x. It's really remarkable that, it could be the case that we have a function whose derivative is actually the same function. That would be really incredible. Well, let's not, take this as being guaranteed yet. Let's actually go ahead and find the true limit, the true derivative of e to the x using our limit definition. But with this in mind, now we have some sort of idea what it is we're looking for, and we'll be able to kind of prepare for that as we move along. Okay, so now we're going to apply the limit definition to find the derivative and hopefully to prove what we have kind of discovered in looking at the graph. So the derivative with respect to x of the function e to the x as defined by our limit. And you can use whichever limit definition you want, although I think this works particularly nicely with the standard definition. So the limit as h approaches 0, e to the x plus h minus e to the x over h. Okay. Remember, we can try first plugging in the value. If we do that, we're going to get 0 over 0. So what we need to think about is how can we, maybe try and algebraically manipulate this situation here so that, maybe we can factor some things out, or, have something that maybe we can think more clearly about. And if we look to the numerator, what you might notice is that I have something to a power that incorporates a sum. So as an example of this, what if you had 4 raised to the 3 plus 1? Well, that's just 4 to the 3 times 4 to the 1, right? Because it's 4 to the 4. So 4 to the 3 times 4 to the 1. Okay, so that means that e to the x plus h is e to the x times e to the h. And then when you multiply those out, you'd add the exponents together. So we can rewrite this function, or I'm sorry, our limit statement, as e to the x, e to the h, minus e to the x over h. All right. Well, now think about one of the hints was that if you can factor anything out of the limit that does not actually depend on h, right? So it will never actually change. As h approaches 0, what's never going to change? Well, e to the x, notice, that doesn't depend on h at all. It just depends on x. So if we can actually factor out this e to the x, we'll only have something that depends on h. And in fact, we can. This term has an e to the x, and this term has an e to the x. I'm going to go this way so we have more space. So that'll be e to the x times e to the h minus 1 over h. And what we talked about previously in one of our limit properties is that if you have a limit which is looking at how some value, some variable approaches a number, in this case it's how h approaches 0, and there's something in your limit that is not involving h, in other words, it's independent of h, which is the case for e to the x, we can factor that out because it's not going to change at all when you take the limit. You're still going to be multiplying by it. So we can actually factor this out of the limit, so we have a slightly cleaner limit. Okay. At this point, it's important to think about what the situation that we've come up with is. We have e to the x times some limit here. When we go back and we think about what we hypothesized previously about what the derivative of e to the x should be, we came up with a function that looked and felt eerily similar to the original function. And notice, as I'm taking the derivative, I'm expecting to get something eerily similar, and at this point, I have e to the x already as a part of my expression. The only other thing I have is this limit. What would be really helpful for this limit to be equal to if I expect my derivative to be eerily similar to the original function? And so you might be thinking to yourself, well, what about if it was 1? If this limit was 1, then we just have e to the x. That would be pretty great. So can we evaluate this limit? Well, if I plug 0 in for h, I'm going to get e to the 0, which is 1 minus 1 over 0. Again, 0 over 0. So I could try algebraically manipulating here. I'd need to pull out an h value. But we haven't really learned, at least I can't recall, a way of pulling out an h if I have e to the h. So algebraic manipulation fails us. What is our next recourse? Let's make a table or look at a graph. So if you were to graph the function e to the h minus 1 over h, and you could use in your calculator, you could use the variable x, or if you type this into Wolfram Alpha, you could use the variable h and it would figure it out for you. And then look at what's happening as h approaches 0. Or you could make a table of values, right, as you approach 0 from the left and as you approach 0 from the right, plugging it into this function and seeing what you get. So why don't you go ahead and do that right now and see if you can conclude what this limit should be equal to. Okay, so the first thing I did was I made a table of values, used my calculator here, and what I found is that as I approached, and so y here represents the value of e to the h minus 1 over h, and x represents the value of h, just in case you're wondering. You can add that to your notes if you need. As I'm approaching 0 from the left side with negative numbers, these are the y values that I get. As I approach from the right-hand side with positive values, these are the values I get. And of course, when I plug in 0, I get an error, because I'm taking the limit. I know already that I'm expecting it to be undefined. What do these values appear to be getting closer to? You might hypothesize they're getting closer to 1. Let's take a look at the graph to confirm. So I've gone on Wolfram Alpha and pulled up the graph of e to the h minus 1 over h. And here's what it looks like. Notice, as I approach an x value, or an h value, I should say, this is the h. As I approach an h value of 0 from the left, and as I approach from the right, pretty darn clear that the value of my function is approaching 1. And this is a pretty big result, because with this result, what I am finding is that this limit here is equal to 1. And so the value of my derivative is e to the x times 1, which of course is just e to the x. And so what we've just proven is that the derivative of the function e to the x is itself. In other words, this function is its own derivative. What we hypothesized, we were able to prove, and it's pretty remarkable. Which means that not only can you find the value of the function e to the x at any point by evaluating e to the x, but in fact, you're also finding the value of the slope at that exact point, which is quite remarkable. Okay, so let's go ahead and put this into formal writing and apply it into some cases. Okay, so the derivative of e to the x, so for the function e to the x, the derivative of e to the x is e to the x. Nothing too special. However, there is a case that we haven't talked about, which is just like with the chain rule, when you took a number and you raised it to some power, you got a polynomial, you could have an expression that involves some other things going on in the exponent here. So how do we handle that situation? And an example of this would be, how do you take the derivative with respect to x of e to the 2x, for example? Okay, so we need a theorem to deal with this, and I encourage you to think about what this would be on your own in thinking about what we just learned about the chain rule, but it shouldn't be too complicated when you see it. Okay, so as we saw previously in that example that I wrote up here, you could have some function e raised to a power, where that power is itself some function of x. Something is actually happening to x there, as opposed to it just being x. And so if u is a differentiable function of x, then the derivative with respect to x of e to that function is equal to e to that function, of course we've seen that previously, times the derivative of u with respect to x, meaning times the derivative of this function with respect to x. So you can think of this du dx, this is taking the derivative with respect to x of our function u of x. Okay? It's this piece right here. Okay, so let's take a look at a quick example here. If I want to take the derivative with respect to x of e to the 2x, what I want to do first is take a look at my situation here. I have e raised to some power, which itself is a function of x, right? This is some function 2 times x. And so I can actually take the derivative of this on its own with respect to x. So the derivative of this whole function will first be e to whatever it's raised to, which is e to the 2x, times the derivative of this upper part, the derivative with respect to x of 2x. Well, that's just going to be e to the 2x. The derivative of 2x is 2, so times 2, which means that the derivative of this is 2e to the 2x. And this should make sense based on what we've seen with the chain rule for polynomials, is that if you have two things within your function, this is a composition of functions, then what you need to do is analyze the derivative of both pieces. So you can't just take, the derivative that we talked about with e to the x, because this is actually e to the 2x, so there's actually a way in which the function is changing just based on how the exponent is changing relative to x. And so you have to take the derivative of that other piece as well, so that when you're writing your derivative, you're actually encapsulating all of this change that is affected on the variable y with respect to x. Okay, so let's go ahead and take a look at one more case, and then we'll get some practice in. Okay, so let's say that we took a function where it was an exponential function, but the base of our function was not e. It was just some value a. And so this is just a typical exponential function. You could think of it as 2 to the 3x or something like that. So for any function a to the u where a is greater than 0, because if it was less than 0, then we have a negative raised to different powers, and that can sometimes be a non-real number. It gets weird. A not equal to 1, because if this were 1, then it would just be the number 1 always. It's a constant function. And u is a differentiable function of x, right? That just means that this exponent is some function of x, has x involved. Then the derivative of a to the u is a to the u times the natural log of a times du dx. So there's a couple pieces involved here, and I want to talk about where they come from. The first is that you notice we have this du dx at the end. This is just the derivative of the exponent, right? That's what we saw with e to the u. You find you're taking the derivative of this whole thing, a to the u, and when we were taking the derivative of this whole thing, e to the u, we knew that the derivative of e to the u was just e to the u. So we had that derivative, but we also had to incorporate the derivative of the exponent. And so here, we have to also incorporate the derivative of the exponent. So at the end, we'll multiply by du dx. Which leads us to, why is the derivative of a to the u, where does this a to the u times ln of a come from? And so I want to walk you through that briefly, so that you just have a conceptual understanding that I'm not just making this completely up. Okay, so this is kind of a proof. It's not the most rigorous of proofs, but I want to show you where this comes from. So if I have some function a to the x and I want to differentiate it, remember that we already have a rule and a way for differentiating e to the x. So if I can somehow rewrite this where it's in terms of e to the something, then I'm in good shape. And so the way that I can do that is by taking advantage of the fact that if I have some value and I do this to it, so I take e to the natural log of whatever that value is, it's the same thing. Okay? And here's why. Because the natural log is just saying, what do I raise e to the power of to get a to the x? Okay? Well, whatever that power is, I'm raising e to that power. So I'll end up with a to the x. Okay? So these two are equivalent, and now I have something that I can take the derivative of, because this is e to some, something of x. And I can actually make this a little bit easier, because remember, if you have the natural log of something to a power, you can bring the power to the outside. And so what I have is e to the x ln of a, whatever my base originally was. And I can take the derivative of this. So the derivative with respect to x of a to the x is just going to be the derivative with respect to x of this function, e to the x natural log of a. And we remember from what we just learned that this is going to be e to the x natural log of a times the derivative of this up here. But remember, it's the derivative with respect to x. So think about what that means. Times the derivative with respect to x of x times natural log of a. But a just is some number, right? That was just the base of my exponent. And so the natural log of some number is just some number, which means I can factor it out of my derivative, just take to the derivative of x. Well, the derivative of x is 1. So this whole thing is just ln of a. So what am I left with? Well, let's think about it. What's e to the x ln of a? Oh yeah, that's a to the x. What's the derivative of this? Oh yeah, it's just ln, or natural log of a. So what we've just shown is that the derivative of a to the x is a to the x times natural log of a. So the derivative of a to the u is just going to be a to the u times natural log of a. And because this could be a function of x, not just 1 times x, I've got to take the derivative of the exponent with respect to x and multiply it out front. Okay? Just as we saw here, we took the derivative, and it just turns out that when your exponent is x, the derivative of that is 1. And so you're going to end up with times 1 over here. So that's why this works out. All right, I'm going to give you some problems to practice, and you can go ahead and apply these theorems. Okay, so here are some for you to practice. Go ahead and give these a try. Make sure to confirm your answer graphically for number 4.